Okay. So, let us come towards the last part of this discussion. We have done complete discussion, theoretical discussion and the design on axial flow turbine. Now, there are couple of small components which are left. One will do a quick discussion on radial flow turbine, and then finally, we will look at the compression turbine matching. So, this is what we are going to talk about on radial flow turbine. So, this is typically like your similar to your centrifugal compressor, where you have the fluid here fluid enters and leaves in two perpendicular directions. Okay. So, the here also for radial turbine the flow enters radially and leaves axially close to axis of rotation. So, the turning of the flow takes place in rotor passage, which is relatively long and narrow, and for small mass flow rate the radial turbine is efficient for small mass flow rate, and which is relatively also this is better or rather preferred compared to axial one. So, this produces also high develops high pressure ratio per stage. So, high expansion ratio per stage, this is compared to axial one, but obviously, when you talk about the radial one the multi staging would be a problem, but with the axial one we can go for multi staging and can produce high expansion ratio. So, these are used in typically in turbo chargers for small gas turbines, turbocharger for cars, buses, trucks, railway locomotives and diesel power generator, cryogenic and process expander. Okay. Now, also apart from the radial there could be another type which is called the mixed flow machine or mixed flow turbine. Okay. So, that is characterized is a combination. So, this is a combination of axial plus radial type. Okay. So, radial flow turbine is composed. So, now when you talk about radial one, this has 4 elements. So, like volute, this we have already seen for centrifugal, then the nozzle vanes, rotor, diffuser, or sometimes this can be identified as a exducer. So, flow enters the diffuser at a large radius and leaves in a smaller radius. Okay. So, now we can look at the quick aerothermodynamics of the turbine, but let us see this a plot quickly. This is already we have. So, this okay, and this goes with an and then it goes like this. So, we have some like that. Similarly, this side also we have, and this is connected. So, this is also connected. So, this is the direction of the flow and there are different station number. So, let us say this is 1, this is 2, this is rotor blade, this is the stator blade, flow goes out like this. So, this is station 3, this is station 4. So, these are the station number that we can use, and at the same time we can see the TS diagram. So, the TS diagram, so that our analysis would be much easier once we look at the TS diagram. So, that is 1, from 1 it comes to 2. So, then 2 to 3, so this is P1, then you can have P01, P02, we can connect them from here. So, let's this is P02 and this is P01. So, these are the connecting lines, this is 1, this is 2, this is 3 and 3 to 4. So, this is P3, so this could be PA, this is P2 and then this is P02 relative. So, from 1 if I come down, so these are extended. So, these are 2 prime, 4 prime, 3 prime, 3 double prime, then we could have from 3 there is a line which is called 3 relative, and then this is P03, then we can have P04. Okay. So, this is 02, this is 01. So, this point is V1 square by 2 Cp and this is V2 square by 2 Cp. Now, this is 03. So, this is V3 square by 2 Cp. Now, this is W3 square by 2 Cp. This is W2 square by 2 Cp. So, these are the things, and velocity triangle if we draw. So, this is how we can draw it. So, that is W2, alpha 2, beta 2, V2, E2. So, this is U3, beta 3, V3, W3. So, we have the both the velocity triangle and the TS diagram. Now, as no work done in the nozzle, so we get H naught 1 equals to H naught 2. Now, the stagnation pressure drops from P naught 1 to P naught 2. This is due to irreversibilities. So, the specific work given by the Euler turbine equation, W would be U 2 V theta 2 minus U 3 V theta 3. So, this is what we get, and we can write this as same H naught 2 minus H naught 3, which can be written C p T naught 1 minus T naught 3. So, now if the flow at the rotor inlet is radial, so the flow at the rotor inlet is radial, then the relative angle beta 2 would be 0. So, we get thus we have U 2 equals to V theta 2. So, sorry V z 2. So, we get W equals to U 2 square minus U 3 V theta 3. If the swell velocity is 0 at the exit, then we write W equals to U 2 V theta 2, and if the flow is radial at the inlet and axial at the outlet, so also we get W equals to U 2 square. Okay. So, now we can look at the spouting velocity, which is V naught. So, this term spouting velocity originally came from the hydraulic turbine design practice. This is defined as the velocity that has associated kinetic energy equal to the isentropic enthalpy. So, this is associated kinetic energy equal to the isentropic enthalpy drop from turbine inlet stagnation pressure P naught 1 to final pressure. The exhaust pressure here can have several interpretation depending upon whether the total or static conditions are used in the related efficiency definition, and upon whether or not a diffuser is included in the turbine. Thus, if the flow is assumed ideal isentropic through the turbine with specific diffuser, then the specific work can be defined as H naught 1 minus H 4 s, where this V naught is the spouting velocity, and this could be related or equivalent to the isentropic enthalpy dot. So, U 2 square would be V naught square by 2. So, the velocity ratio what we get U 2 by V naught would be around 707. In practice, this lies between 0.68 to 0.71. So, that is how it lies between. When no diffuser is used and if the total condition are used instead of static, then we can using static condition, you get V naught square by 2 is H naught 1 minus H naught 3 S s, which is C p T naught 1 minus T naught 3 S s. Okay. Similarly, there are efficiencies for radial flow turbine, which can be defined. One is the turbine total to static efficiency, which will be T naught 1 minus T naught 3, T naught 1 minus T 3 prime, which is delta T naught by T naught 1 minus T 3 prime. These are all corresponding to that HS diagram. Total to total efficiency, this is T naught 1 minus T naught 3, T naught 1 minus T naught 3 s. So, which is delta T naught minus T naught 3 s. So, the combined efficiency or the overall efficiency is T naught minus T naught 3 prime delta T naught by T naught 1 minus T 4 prime. Now, there are also losses, like we can have nozzle coefficient losses. So, which is nozzle coefficient loss is defined as T2 minus T2 prime by B2 square by Cp, assuming T2 T2 minus T2 prime is T3 double prime minus T3 prime. So, we can replace that T3 double prime minus T3 prime B2 square by Cp T2 prime by T3 prime. Now, rotor loss coefficients, this could be also written as T3 minus T3 double prime W3 square by Cp. So, this can be used. Now, there are some dimensionless parameter. One is stage loading, which is psi delta H naught by U2 square. So, these are similarly that we have defined for axial case, and this one can show that this would be V theta 2 by U2. There could be flow coefficient, which is Bz 3 by U2, rotor non-dimensional velocity. So, this is Br2 by Bz 3, which would be roughly 1, and the specific feed was applied almost exclusively to incompressible flow machine, and which is defined as N Q by delta H naught S 3 by 4. So, this is the volume flow rate, this Q is the volume flow rate at the outlet. So, one can have some recommended design practice. So, based on the design, first you need to calculate the stage loading, which is would be range of 0.8 to 1. Then you can design some flow coefficient, which would be range of 0.3 to 4. Then you have total to total and all the efficiency, total to total, total to static efficiencies would be greater than 0.7. You have velocity ratio, which would be close to 1. Then the ratio between hub to inlet radius, which would be also range of 0.25 to 0.35. And now, finally, if you compare both the axial and radial, so the axial quick comparison and radial, the axial one is used for large engine, this is used for small engine, this is for large, this is for axial for large mass flow rate, this is for small mass flow rates, better efficiency, this has lower efficiency, low pressure ratio per stage, this has high pressure ratio per stage, higher overall efficiency, lower overall efficiency, multi-staging is possible, multi-staging is difficult, very expensive, it is cheap, difficult to manufacture, this is easy to manufacture. So, these are the some of the comparisons that one can think about between this. Now, finally, we go to the gas turbine engine matching. So, this is like we have to take the first the compatibility condition, compatibility conditions. So, we have operating speed n by T naught I for turbine would be n by T naught I compressor into T naught I compressor by T naught I turbine, okay, where I stands for inlet, and now we will use T for turbine, C for compressor, and then this could be written 1 by T naught I turbine equals to 1 by T naught I C into T naught I C by T naught I T. Mass flow rate, so this could be m dot T, T naught I T, which will be P naught I T would be m dot C, T naught I C by into P naught I C by P naught E C, P naught E C by P naught I T into T naught I T by T naught I C into m dot T by m dot C. So, E stands for outlet or exit condition. Now, the compressor pressure ratio is pi C, which is P naught E C by P naught I C, and combustion chamber pressure ratio pi C C, which is P naught I by turbine by P naught E compressor. Conservation of mass, which we will get m dot T equals to m dot C plus 1 plus F minus B. F is fuel air ratio, this is bleed to air ratio. Then we can have conservation of energy or power balance. Now, just to look at some single shaft gas turbine engine. So, these are the following steps. You select a rotational speed n, so that the from ambient conditions we can calculate n by root T naught 1, which define the speed lines. Then you can compressor pressure ratio, assume this P naught by P naught 1. From the compressor map we can find the operating point and the mass flow rate parameter like m dot by root T m dot root T naught 1 by P naught 1 m dot root T naught 1 by P naught 1 and compressor efficiency. Then the compressor mass flow rate is calculated by this relation m dot by root T naught 1 by P 1 into P 1 by root T naught 1, and then the turbine mass flow rate is calculated 1 plus this would be into F minus B, and we calculate the specific work of the compressor, which is CPC T naught 1 by eta C, P naught 2 by P naught 1, gamma minus 1 by gamma minus 1. So, that is how you calculate. So, from the map you get all this. Then you get the pressure loss in the combustion chamber, which is P naught 3 is P naught 2 into 1 minus delta P C C. Then assume the turbine inlet temperature T naught 3, we calculate n by root T naught 3 and which is equals to n by root T naught 1 into T naught 1 by T naught 3. So, this will determine the speed line for the turbine map, and then finally turbine mass flow rate is determined m dot 3 by T naught 3 by P naught 3, which would be m dot 1 T naught 1 by P naught 1 into T naught 3 by T naught 1, P naught 1 by P naught 2, P naught 2 by P naught 3, m dot 3 by m dot 1. Now, from this mass flow rate parameter and operating speed line, the turbine efficiency can be calculated from the specific work which is output for the turbine would be eta T CPT T naught 3 1 minus 1 by P naught 3 by P naught 4 gamma minus 1 by gamma, and then finally the power would be m dot 3 W T minus m dot 1 W C by eta m. So, a check has to be performed, so that you can. So, this is for a single stage single shaft engine one can do. Then one can have off design of free turbine engine also. Free turbine engines which is like an gas generator, and similarly you can find out this mapping, and then this is used for these things. So, the free turbine or the gas generator also one can do like so these are the steps. First you can select some speed line on the compressor map and choose any point on line. So, on the compressor parameter like n by, so these are one has to choose P naught 1 m dot 1 by T naught 1 divided by P naught 1 and eta c. So, when you choose that, then you finally calculate the compressor specific output, this is calculated, then you guess some value of pressure ratio for turbine and the value of the turbine mass flow rate through the turbine m dot T, this should be calculated with this guess value, and the turbine mass flow rate is once it is determined, already we have shown the equation, then the turbine mass flow rate which is kind of mapped with the compressor, that can be done, which is exposed like m dot 3 T naught 3 by P naught 3 into m dot 1 by T naught 1 by P naught 1 root T naught 3 T naught 1 m dot 3 by m dot 1. So, then next step, so turbine inlet temperature could be defined. So, this would be can be defined and which the speed line of n by T naught 3 or turbine efficiency, that can be determined. Then finally, we can match the temperature ratio and then find out the other procedure or the steps to follow, which we have already shown, find the output of the turbine power and like we have done, and the total power. So, essentially this is how the mapping is done. You first assume certain parameters, then go to compressor map, pick up some values, then go to turbine, calculate everything, then match the mass flow rate, because the mass flow rate has to be properly mapped, and then finally look at the inlet temperature, what has been assumed, that is correct or not, and once this converges you find out the power and the turbine. So, that is how one do the mapping for the compressor and turbine, and this is also very important, the compressor and turbine mapping, because these are important for the design of the gas turbine unit. So, if you look at that, we have first initially looked at the cycle analysis, then when you move to the rotating component like turbo machineries, we have looked at axial compressor, axial centrifugal compressor, axial turbine, to some discussion on radial turbine, and finally this mapping. The whole point is that turbine produces the power, and some of the power which is produced by the turbine, it goes to operate the fan and the compressor in the gas turbine engine, and that is why this mapping is very important, because they have particular characteristics of operational line and this should restrict their operation. So, that pretty much concludes the theoretical discussion of all these air breathing propulsion. Thank you very much.